So, one of the things that we have done previously is to represent switching network as propositions. And we're doing that because if we can write our switching network as a proposition, then we can have the truth table of those propositions as closure tables for the given switching network. So, what is a closure table? A closure table are used, or closure tables rather, are used to determine under what condition a switching network is open or closed. In the closure table, 1 signifies that a switch or a switching network is closed and 0 to indicate that it is open. Remember that in previous videos, we have talked about that this does not mean that it is the usual notion of our network or switch rather, but again, 1 signifies that it's closed because current can flow. Current can flow. So again, this is not our usual or common notion of a switch that 1 signifies it's open. So remember, 1, there you go, 1 signifies that it's closed and 0 signifies that it is open. So we have to remember that. And the closure table is exactly like a truth table. Since we're making an analogy between propositions and switching networks, we're going to do exactly that. We're going to also make an analogy between closure tables and truth tables. So before we go to that, we have to remember the following notions. So first, if this is P, if this is switch P, this is switch not P. So we have to remember now what will be our truth table or closure table for these switches. So we would have P and we would have not P. And we know that if it's P, there's only one, so it can either be just close or open, true or false. And if P is close, therefore the switch not P would be open. And if switch P is open, then switch not P would be closed. Very similar to our negation. If P is true, then not P is false, and vice versa. So here we have our series network, and we know that our series network is related to conjunction. So that means if we would have P and Q for our truth table, let's just rewrite that so that it's easier seeing. Let's erase this first, and we'll have here, this is our P, Q, then our P and Q. So we'll have our usual numbers for truth table, 1 1 0 0 1 0 1 0. So therefore we know that a conjunction will be true if both are true while the rest would be false. So similarly, this network, this series network will be closed if both switches are closed. Well, that makes sense because if this is closed and this is closed, current can flow. But if this is closed but this is not closed, hence open, the current cannot flow. Very similar to the truth values of our truth table for conjunction. Finally, we have the parallel network, which is similar to disjunction. So we can have P and Q again, and then we'll have P or Q. 1 1 0 0 1 0 1 0 and 1 0 1 0. And for this junction first, this is true if at least one of the propositions are true. So that's true, this is true, true. And the only time a disjunction is false is if both propositions are false. So similarly, in a parallel network, it is closed as long as one of the switches is closed. Because as we can see, if this is closed here, so it flows, and if it's closed here, then it flows there as well. However, if it's open, let's say in P, then this gets cut. Let's erase that to represent that it gets cut. There you go, this gets cut, but the flow, or the current rather, can still flow through Q and hence go out. Similar if this Q was closed. So that's why a this is a parallel network, is very similar, or similar, not just very, but actually similar to the values of a disjunction. And this is also why a parallel network is analogous to a disjunction. A series network is analogous to a conjunction because of the truth values of our truth tables, which corresponds to the values in our closure tables. So we're going to use this knowledge in analyzing as to when a switching network is closed or not. And we're going to have examples in our next video.